This is the interim presentation for the ME 4056 Refrigeration Lab given by Group D.
The purpose of this week's lab is to model a cooling system based on a vortex tube that uses air as a working fluid. The experimental setup is shown in the figure on the right. Station 1 measures compressed air coming into the system before the air enters the heat exchanger, marked as number 2. In the heat exchanger, the air is cooled to the ambient temperature of the room. The air then enters an accumulator tank, marked by 3, where variations in pressure are evened out. When the air exits the accumulator tank, the pressure should be stable and the temperature should be at the ambient. The air then enters the vortex tube, which has 2 outputs, a hot output and a cold output. On the hot side, the hot output from the vortex tube is at ambient pressure but an elevated temperature and vents to the atmosphere. On the cold side, the cold output from the vortex tube feeds to an aluminum block with an internal heat exchanger. This allows the air to cool the block. The block is insulated, though some heat transfer will still occur due to the differential between the ambient temperature and the temperature of the block. The output of the block measures the temperature and pressure of the air just before it is vented to the ambient. The pressure at this sensor, marked as number 5, is at atmospheric pressure, though its temperature will be lower due to the cooling effect of the block. Flow rate sensors are present at the outlet of each exit point of the system to measure the rate at which hot air and cold air exit the cooling system. For this first week of testing, we focus exclusively on the cooling system, using a stable, building compressed air source.
As the air is pumped through the system, data on the temperature, pressure, and flow rate are captured. Then, by splitting the plots into sections based around where the data reaches steady state and averaging those datasets, the respective steady state values were found and tabulated above. After tabulating the steady-state values at each pressure, York regression plots were created depicting the baseline curve of the natural log of each parameter versus the natural log of the pressure along with the relative uncertainties. The primary reason for plotting these values as natural logs was to simplify the process of finding the necessary parameters for the system cooling equation broken down later in the presentation. York fit is used on the natural log of the temperature of cold air at gate 4, hot air also at gate 4, vortex tube cold output mass flow rate, and the hot output mass flow rate in the vortex as well, in order to determine their relationship with the pressure at gate 3. We had to assume that gate 5 temperature was equivalent to the ambient temperature. Uncertainty analysis was also performed, represented with the ellipses included in the plots. The equations to the right of the plots are the correct error propagation analysis equations for MC dot and MH dot. We, however, had to only take the first component from these equations, underlined in red, because the full equation would yield uncertainties that were clearly incorrect and affected our plots.
The thermal resistance is calculated by taking advantage of the fact that Q dot air is equal to Q dot ambient during steady state. The equations for Q dot air and Q dot ambient can be equated to each other and rearranged to isolate for and solve for thermal resistance of the insulation, which can be seen on the slide labeled as experimentally calculated thermal resistance. The steady-state regions of the data were found by plotting the load temperature with respect to time and selecting the range of values where local load temperature does not change significantly with time. The theoretical thermal resistance was calculated by using the given formula that the thickness of the insulation divided by the surface area of the insulation multiplied by the thermal conductivity equals thermal resistance. As can be seen on the slide, there is a large difference between the theoretical value and the experimentally calculated values. This can be partially explained by the picture of the block to the right. The block is not fully insulated, as there is uninsulated space on the top of the block where air goes in and out. This space decreases the thermal resistance value. When doing the theoretical calculations, it was assumed that the entire block was covered in the insulation, which is not accurate. This is an example of an error occurring due to model simplification.
One of our goals was to determine how well our system fit the general system cooling equation. The first step to achieve this was to use a York regression on the linear region of the data for the load temperature as it varied with time for each of the two P3 pressures of 50 psi and 80 psi. This region was the transient region, which we would later also use for our experimental calculation of the load's mass. From the York regression, we were able to get the parameters tau and beta for both of the experiments. These results were a value of 775.9 and 30.03 for the 50 psi experiments tau and beta respectively, and 466 and 20.45 for the 80 psi experiments tau and beta respectively. Something that is important to note here is that the uncertainty for our tau values do not make sense with our calculated value of tau. We believe that this is a propagation of the problem that we mentioned regarding the error propagation analysis equations for our vortex tube uncertainty analysis. Our calculation for the effective mass of the load was the next step to determine how well our model fit the system. For this calculation, we relied on the equations for the heat transfer rate to air and that for the energy change rate of the mass in the transient region of our datasets. Both of these are shown in this slide. The partial derivative of the Bloch's temperature with respect to time was found using the slope for the York regression that was shown in the previous slide. By using data in the transient region, where the heat transfer rate due to the ambient heating is taken to be 0, we can set these equations equal to each other in order to solve for the mass of the block. Our results were a mass of 4.35 plus minus 0.44 and 4.81 plus minus 0.40 kilograms from the 50 psi and 80 psi data sets respectively. The measured mass was of 0.4543 kilograms, which means that our experimental calculation is off by approximately a factor of 10. This big error in our experimental results is likely not due to our uncertainties from our equipment, but instead due to the assumptions and simplifications that we made on our model. A very big part of this error is the fact that there is always going to be heat transfer between our load and the surroundings, even in the transient region, while we assumed it to be 0 in our model. The insulation will not be enough to make this assumption true, particularly at the top where the load remains exposed during the experiment.